Hi, welcome to CSC 114, Introduction to Object-Oriented Programming. The topic of this lecture is Recursion Part 2. So in this lecture, let's start with another interesting example involving recursion. And here we are looking at Fibonacci numbers. So now Fibonacci numbers that we have are associated with a series. So sometimes people call it Fibonacci numbers, and it is also referred by another name, which is Fibonacci series. So let's try to understand how is this series formed. So here in the right here you have these Fibonacci numbers in the sequence or the series, right? And on the top we have something called as indices. Now what is the significance of indices here? So indices are just signifying the fact that the first number in the Fibonacci sequence is 0. So if you represent the Fibonacci sequence in an array, then at the index 0 you'll have the first element, which is 0. The second number in the Fibonacci series is number 1, and that will have the index 1 if you store Fibonacci series in an array. Then the third number with the index 2 has the value 1. The fourth number has the value 2. The fifth one is 3. Sixth one is 5. Seventh one is 8. And then the eighth one is 13. Now this eighth number would correspond to the index 7, and its value is 13. The ninth one is 21. 10th is 34. 11th is 55, and 12th is 89, and you have the numbers in the sequence. Now the interesting aspect of the Fibonacci sequence is that the number at the ith position, like this number 1, is equal to the sum of the number in previous two positions. So I can generalize it. If I'm looking for a Fibonacci number at position n, then that will be equal to the sum of the number in the position n minus 2 plus the Fibonacci number at n minus 1, right? So if you want to find out the number at nth position, Fibonacci number at the nth position, then you can easily find by adding the number at n minus 2 position and at n minus 1 position in the Fibonacci sequence. So let's see whether this is applicable or not. So the number 1 that you have at the third position is equal to 0 plus 1. Now the number which is at the fourth position is equal to 1 plus 1, which is 2. The number at the fifth position is 2 plus 1, 3. The number at sixth position is 2 plus 3, 5. And then so on and so forth. This number 8 is equal to 3 plus 5. The number 13 is equal to 5 plus 8, right? So that's how the Fibonacci sequence or the series is formed. Right. So now let's see how is the recursive formulation getting into it. Right. So here, if you pay attention, then you can identify the recursive formulation. Right. So if you ask me the Fibonacci number at the nth position in the series, then that fn is equal to f of n minus 2 plus f of n minus 1. So here f stands for Fibonacci number. All right, so what else do we have? Well, we do have these numbers at the position 0. So for Fibonacci series, we know that the first number which is at the index 0 is 0, and the second number which is at index 1 is 1, right? So we know that the initial two numbers are 0 and 1 respectively. Now when I know what is f of 0, what is f of 1, right, then I can find out f of 2, right? So this is 0, this is 1, so I know f of 2 is 1, right? So fib 0 and fib 1 are the base cases. In the recursion, we do need something called as the base case. So in a Fibonacci sequence, we have two base cases, fib of 0 and fib of 1. So when I'm saying f of fib, then please treat f and fib as equivalent. Both are referring to the Fibonacci number in the sequence, in the Fibonacci series or the Fibonacci sequence. All right, so here we go. Right now we have the formulation where the Fibonacci number at the index will be equal to Fibonacci number at index minus 1 plus the Fibonacci number at index minus 2. And this is the relationship, this recursive relationship that you have over here is applicable for index greater than or equal to 2. For index 0 we know that is 0, and for index 1 we know that its value is 1, right? So those are the base cases over here. All right, so if we have to find out the Fibonacci number at a position, say 3, then for that I'll have to do it like a fib of 2 plus fib of 1, and fib of 1 I know is 1, right? But now I need to solve for fib of 2, and fib of 2 is equal to fib of 1 plus fib of 0, right? So you can see recursion over here. Now I know fib of 1 is 1, fib of 0 is 0, so that would compute the fib of 2, right? Then I know fib of 1, which is 1, so therefore fib of 3 is equal to 1 plus 1, which is 2. All right, so what next? Well, now we need to write a program for computing Fibonacci number, right? So what I'll do before I walk you through this code on the lecture slide, I would try to do this on an IDE as a demo, right? So let's quickly hop over to the IDE. Okay, so for this thing, let me delete this guy from here, and I would rather write public static int Fibonacci. All right, and here somebody should give me the index, right? So the Fibonacci number I will generate for a specific index. Now how should I do that? Well, let's start. Well, I don't have anything in the main method. Well, if you want that, then let's think about main method first. So I should say import java.util.scanner. The reason being, we would let the user tell us like what index Fibonacci sequence the user wants to get, right? So let's create a scanner object. Scanner input is equal to new scanner system.in. All right, now we will from the user enter the index of Fibonacci number. All right, and then let's declare index as the variable which will get the integer input from the user, and let's invoke the next int method on input variable, and I would also close this object input. Okay, cool. So now let's worry about Fibonacci, and then we would invoke this Fibonacci method from the main method. All right, so we know the base condition, right? What we know is that if index is equal to 0, then we need to return 0. As if index is equal to 1, we return 1. As what we do, well, now is the interesting thing. As return what? Now we will apply the recursive formulation as return Fibonacci of n minus 1 plus Fibonacci of n minus 2. All right, yes, sorry, I should not say n. In place of n I should use index. Right, so there's nothing like n for this method, right? The formal parameter has been named index. All right, so here we have the interesting part, which is the statement number 15, and that's where we are making two recursive calls. The first one is Fibonacci with index minus 1 as the parameter, plus the second recursive call is for Fibonacci with the parameter index minus 2, and this is all based on what we have here in the lecture slide, right? This formulation, fib of index is equal to fib of index minus 1 plus fib of index minus 2. All right, let's go back to this program now. So how should I invoke? Well, it's we'll say that, right, the Fibonacci number at index. What index? Well, for that we'll use index variable is, right, let's separate that. And now, you know what, let me break it down in 2 lines. Wait a second, right? Wait a second, right? This should be a line before this is out, right? Because at this line number 7, we should know what is INDX, and INDX has been defined on line number 6. So what I do here, let me break it down in 2 lines. Is now we will invoke this method Fibonacci and then INDX. All right, so we are almost done. So let's run this program. Okay, so let's find out the Fibonacci number at position 2. Right, at position 2 is 1. Why 1? Because see, this is position number 2, right? Yeah, at position 2, this is the number. 0 plus 1 is 2, right? When index is equal to 0, then the value is 0. When the index is equal to 1, the value is 1. When index is equal to 2, the value is 1, right? So let's find out now the value for index number, say 7, right? So that will be interesting. So when I run it for value 7, I got 13, right? So let's check that, right? So the 7th position is 13. Let's do it for 11 now. When you run it for the index value as 11, you got 89, right? So we are done. All right, so for the explanation, I'll take you to my lecture slides. Okay, so the same program we will recap systematically in this lecture slide. So here is the class that we have written for Fibonacci, and we are calling this class as Compute Fibonacci. It's a public class, Compute Fibonacci, and we are using scanner class, importing scanner from java.util package. And here is the opening and closing brace for this Compute Fibonacci class. Now here we would need a main method, right? The main method has been defined the way we do. It's public static void main, and it has the parameter which is a string array called args. So here we will create input, which is a scanner object, by saying new scanner system.n, and now we are prompting the user to enter an index for Fibonacci number, and that has been captured or stored in the variable index, which is of type int, and you are saying input.next int, and then you invoke this method fib on the index. All right, and you're printing out that the Fibonacci of index is this value. Now let's pay attention to this interesting recursive method called fib. Right, so here we are saying public static long. It has been declared of type long because you know, as the index you know, goes bigger and bigger, you would expect a bigger integer value. For that reason, the return type for fib has been here declared as long. When I did the demo, I kept that as an integer, but it's better if you declare its return type as long. All right, so now we are taking care of the base case. When index is equal to 0, you return 0. Else if index is 1, you return 1. And For other cases, when the index is not 0 and 1, now we'll have to do the recursive call. We return fib of index minus 1 plus fib of index minus 2. All right. So now let's look into the recursive phenomena that goes on behind the Fibonacci sequence. So for that, we'll take an example like fib of 4. You had to do fib of 4, then you know, right, the way it has been defined, fib of 4 is equal to fib of 3 plus fib of 2. Now fib of 3 should also be broken down into fib of 2 plus fib of 1. Fib of 2 would be fib of 1 plus fib of 0. So this has been interestingly depicted in this picture over here. So when you say fib of 0, then that is your call number 0, 0th stage, right, when you call fib 4. And fib 4 would be broken down into fib 3 plus fib 2. Now what we are doing here, let's resolve fib 3 first, and we would resolve the later part later, right? So we are doing the left method invocation to this plus operator here. So in the first call, the fib 4 was call 0. Now let's call the let's label the first call as the fib of 3, right? So you have to resolve the fib 3 as well. Okay, so now for fib 3 we are making another call. We are calling that as call 1, or the stage 1 or step 1 when you're calling fib 3. Now fib 3 is again broken down into fib 2 plus fib 1, right? So we would solve fib 1 later. Let's solve fib 2 first. So for solving fib 2, we'll make a second call, right? Or the step number 2 you may call step 0, step 1, step 2. In step 2, you're resolving fib 2, and fib 2 would be broken down into fib 1 plus fib 0. Let's not think about fib 0 for the time being. We will solve fib 1. So for solving fib 1, we are making the third call to fib 1, and fib 1 we know is the value 1, right? So we will return this value 1 for fib 1, and that would be our state step number 4, when you return the value of fib 1. Now since we have solved the left hand side of this plus, we would now come and solve the right hand side of this operation, which is fib of 0. For that, you make the fifth step of calling fib 0, right? And then fib 0 you know is 0. You return that value in the step number 6, right? So now this has been solved, right, which is fib 2 has been computed. You return this value in the step number 7, right? So when you're here, this left hand side has been resolved, but now we need to think about the right hand side of this operation here, plus operation. For that, in the 8th step, you would invoke fib 1, and you know fib 1 is 1, right? In the 9th step, you return that value 1, and you add these values over here. And in the step 10, now you have the computation of fib 3. Fib 3 has been completed here. So you come to this point, and fib 3 computation is complete. You know the value of fib 3. Since this left hand side of the plus operation has been resolved, now we will look into the right hand side, right? So here we returned in step number 10 here. So in step number 11, we will now call fib 2, which will be broken down into fib 1 and fib 0. We will first resolve the left hand side. So in the 12th step, you would call fib 1. In the 13th step, you will know the value of fib 1, which is 1, that will be returned. And now this left hand side of the plus operation has been resolved. Now we'll think about the right hand side of this expression. So for that, in the step number 14, you would invoke fib 0, and in step number 15, it will return the value of fib 0, which is 0, right? And then only in the 16th step, you will be able to get the value of fib 2. You will add these numbers now, fib 3 and fib 2, for which you have the values, and the 17th step you will have the value for fib 4, right? So from this picture and this discussion, you will realize that the recursion in Fibonacci sequence is pretty slow. Look at this tree, right? So this is called recursive tree, right? So this recursive tree is very time consuming in case of Fibonacci sequence. So the recursion in Fibonacci numbers is pretty slow process. All right. So now since we have seen some examples involving recursion, let's generalize recursive problems. Like, what are the characteristics of recursion? So all the recursive methods have the following characteristics. So let's learn what are these characteristics. Now we'll have one or more base cases, and the base cases are the simplest cases possible of these problems. So in the factorial case, we have just one base case, which is factorial of 0 is 1. Whereas in case of Fibonacci, you just saw that there are two base cases, right? So one or more base cases are there. These are the simplest cases and are used to stop the recursion. If you don't have base cases, then the recursion will continue to run forever, and which is a bad news. So every recursion problem should have a base case. Every recursive call reduces the original problem, bringing it increasingly closer to the base case until it becomes that case itself, right? So that happened in case of factorial and also for the Fibonacci sequence. Whenever you are making recursive call, then the recursive call involves the invocation of the same method with the smaller and smaller parameter. Okay, so if you have to solve a problem recursively, then what we should do in general, to solve a problem using recursion, we need to break it down into subproblems. And if a subproblem and this subproblem should resemble the original problem. So if that is the case, if you could break your problem in such a way that the subproblem resembles the original problem, then you can apply the same approach to solve the subproblem recursively. That's what we did for factorial and also for the Fibonacci sequence or Fibonacci series or Fibonacci numbers. Now, the subproblem is almost the same as the original problem in the nature with a smaller size. Okay. All right, so now let's look at a very simple problem that we'll solve using recursion. And the problem is that we have to print a message n times, right? So how can we print a message n times recursively? So that will be interesting. So we'll break the problem into two subproblems. How are we breaking it? Well, we will print a message one time. So if you have printed a message one time, then you don't need to print it n times again. You have to print n minus remaining times, right? So this n times that you wanted to print a message has been broken into one print plus n minus one print, right? So that's the recursion over here. Print n is equal to 1 plus print n minus 1, right? If I had to write a method print the n and print n minus 1, so I'll do this way. So this problem here is same as the original problem with a smaller size. Initially you were required to print n times. Now after printing it once, you have to print it only n minus 1 times. Okay, and what would be the base case here? Well, the base case is going to be the case where n is equal to 0, meaning that you printed the message n times. You don't need to print it anymore. Okay, so now let's think about the recursive method for printing a message n times. All right, so we have this method which is public static void. It's not returning anything as it has to only print the message. We're calling it nprintln. We can't call it println because println is a method which is which we use in system.out. Right, so we are calling this nprintln, and this would need two parameters: the message, which is of type string, and the times, how many times we want to print it. All right, so here we have the recursive formulation. If the times, right, this is like how many times, it's n thing, right, like how many times we want to print this message. If the times is greater than or equal to 1, what we do? Well, we will print the message once, right? It was greater than 1, so we printed it once, and after printing it once, what we do? We will say nprintln message times minus 1, right? We printed it once, so we want to print it one less time, right? And that is it. That's the complete definition of println method, which is recursive, right? Why recursive? Look at this statement here. after printing the message once, we are invoking this nprintln method one more time at least, with the times -1 as the parameter. All right, and originally this nprintln has been defined for times as the number of times we want to print it. All right, and the first parameter remains the same. The message is the same message over here also. Okay, so now we will do a very interesting problem, which is binary search, and we'll do that recursively. So for binary search, we will break it down to different cases. So now in case 1, what we will do, if the key that we are searching for is less than the middle element, then we are going to recursively search for the key in the first half of the array, right? That's case 1. Case number 2, well, if the key is equal to the middle element, then the search will end there with the match, and that will be, interestingly, our base case. So our base case happens when we are successful in finding out the key, right? And there will be another base case where we fail to find the key, right? So let's not think about it. Anyway, while doing demo, I'll show you, right? So we have seen 2 cases. Case 1, when the key that we are searching for is the item that you are searching for in the list. If the item or the key is less than the middle element, then we are going to recursively search for that in the first half or the lower half of the array, right? Otherwise, if the key is equal to the middle element, then our search will end there, and we would return that index as the matching index. Case number 3 will happen if the key is greater than the middle element. So if that's the case, then we are recursively going to search for that key in the right subarray. Okay, and what I will do now, let me do a demo, and then we'll come back and I'll explain the code again using the lecture slides. All right, so let me quickly hop over to my IDE, and here, well, I need to delete few things. I would first of all delete the Fibonacci code, and then I should delete this invocation, and here all right, so I'll say enter the key to be searched. Enter the key to be searched. All right, and for that, well, I'll call it key. Okay, and here we will need a list, right? So let me create a list. I'll call that data. It should be an array into data, and let me initialize right here to save some time. And the list or the data that we have on which we want to perform binary search, it should be a sorted list. So I'll start with 3, 5, 6, 8, 11, 15, 22, and 25. Let's keep it small, but it is going to work for a bigger list as well. All right, so now let's write this binary search code. So I'll say public static int, because I want to return the index where I found the key, binary search, the name of the method. Okay, and now we need to think about the parameter list. So it will have an array. Let me call that list. Okay, and I'm searching for key. All right, so what I'll do here, well, for the binary search, we need to have some parameters. So there are 2 parameters needed for binary search: the low index, which I will initialize at 0, right, because the smallest index for an array is 0, and then I'll have the high index, that is integer as well. High is equal to list dot length -1. Okay, cool. So what do we have to do next? Now what I'll do something interesting. for the reason that this is how this code has been implemented in our textbook also. So, and this will make our life a lot easier. What I'll do now, I will overload this binary search method, right? How will I overload? Well, just a second. Okay, let's say return binary search, and I'm going to define another binary search, overloaded binary search, which will be the real recursive binary search method, and that method would need two additional parameters, low and, wait a second, right here I should not say this, I should rather, since I'm invoking that method, I'll say list key low and high. Just a second. Okay, and here I'm going to overload this method. Overloading means I'm going to define another binary search method with int low and high, two more parameters. All right, so if you look at this binary search, they are overloaded. Excuse me, name is same, right? But if you look at the parameter list, then this is going to be different. Here you have only two parameters. First is an array of integer, the second is a key. But here we have the list, the key, as well as the indices, the starting index and the end index, which will determine the subarray in which we are doing the binary search. Okay, cool. So what should I do here? Let me, now consider all the possible cases. So if, your low should always be less than high or equal to high. Low is the smallest index, the lowest index, and high is the highest allowed index for search in the array list over here. So what I'll say here, I'll say if high is less than low. That will happen when the array that you were searching for got exhausted. So if that is the case, then we'll return minus low minus 1, right? So the issue here is that we are returning a negative value for the index. Now negative value for an index will signify that we are returning an invalid index. Invalid index means that the element the key that we are searching for is not present in the list, right? Now the point is, if we could have easily returned -1, why are we returning minus low minus 1? Well, that is a practice we follow just for the additional information, that by returning minus low minus 1, we'll get an idea like where exactly we could have found this element if it was present in the list, right? So we are returning two information. Negative index value will say that the key that we are searching for is not present in the list, right? And its magnitude will give us some idea about where exactly that key might have been present in the list. Okay, fine. So what we'll do next else, okay, fine. So we have to check high and low, these two, the index values. If high is less than low, then that means we exhausted the list and the key that we are searching for is not present there. If that is not the case, then that means we have some scope. So for that thing, what we'll do, we'll declare a variable mid, right? And we'll compute its value as low plus high divided by 2. Okay, and now once you have found out the mid, now we will deal with the three cases of the binary search. So what are these three cases? Well, if key is equal to list mid, right? So that's the base case. Return mid, return. Else if now we have two other possibilities, right? The second possibility is if key is less than mid, right? That means if the key that we are searching for is will probably be present in the lower half of the subarray, then we'll have to invoke recursive. Okay, let me call it, we should call these recursive binary search, right? That's so okay, let me call it recursive binary search. Recursive lowercase recursive binary search. Control C. All right, so let's call it recursive binary search. If that is the case, right, if the key is less than the middle element, then we are going to invoke recursive binary search on this list. We are searching for key, and our low remains low, but since we have to confine it to the lower subarray, so the high index should be mid -1. All right, cool. And how about the last case where sorry about that, I should simply copy it and paste it over here, and I will edit this condition here. The last condition is for key greater than list mid. If that's the case, then the key is probably present in the right subarray. And how should I search for right subarray? Well, by updating the low. Now the low should be mid +1. I want to search in the right subarray, so here I'll say mid +1, and the high would remain high, right? I don't want to change anything in the high. Okay, so let's see what we have here. A return statement. There's something. Okay, all right. Okay, so we are almost done, right? So what we have to do here, wait a second, if return, that is the case, int mid is equal to this, if key is equal to list mid, then you would return mid. Else if key is less than list mid, right, then you will do recursive return recursive binary search on list key low mid -1. Perfect. Else if key is what we can say, else, this is fine, else we know the last condition should be this one only, and we are good. This is simpler than what I was doing, and it's taking care of all the three cases. All right, so now we are set. We can search for the element, right? So int position is for the location of the key that you're searching for. Here I should invoke the first method. Let's say recursive search for data and key. All right, so let's now run this program. Okay, so what is the key that you're searching for? Let's search for 11. All right, so okay, we did not print that out. Let me print that thing as well. Key, right? What is the value of key? Key is present at index, right? So here we'll have the index as POS. All right, so let's put that here. Now we'll see some output. Okay, let's run this program. We are searching for 11, and 11 is present at index number 4. Let's check that. 0, 1, 2, 3, and 4. That's perfect, right? Now we'll search for 25. Let's run for it for 25. 25 is present at index 7. So 0, 1, 2, 3, 4, 5, 6, 7. We got it. And now we'll search for a number which is not present in the list. So how about 7, right? So 7 is returning the value negative, right? So negative means it is not a valid index. so it's not present, but right, so -4 means the key 7 is not present in the list. And now let's try to understand this magnitude. So 4 means that 0, 1, 2, 3 and 4. So if you subtract 1, right, so whatever value you get here, which is 4, right, so the convention is that in this unsuccessful search, the negative value that you get for index, that needs to be its module we need to take, and from that we need to subtract 1 to find out the index where that element might be present. So if 7 was present, it would be present at index 0, 1, 2, 0, 1, 2, 3, right? 4 minus 1 is 3, and 8 would be on the right hand side. Okay, so now what I'll do, I'll take you to my lecture slides and we'll look at this in the lecture slide one more time. Okay, so here I'll use my pen. Okay, so here is the class for recursive binary search. In this we have the main binary search, recursive binary search method, which is using only 2 parameters, that is the list in which you have to search and the key that you need to search in the list. Okay, so here you need to define these 2 variables, low and high. Low index is 0 and high is list.length -1. Then we are going to invoke this recursive binary search that we still need to define. That's overloaded one, and for this we have 1, 2, 3, 4 parameters, right? The list in which we are searching for key and with the low and high index values. Okay, so now let's look into this recursive binary search, right? The real recursive binary search method. This is the supporting method for binary search. Okay, and here it has the first parameter, which is the list, then the key that you're searching for, the low index and the high index. All right, so we are taking the first case, the case where we are exhausted with the list and we did not find it. When will that happen? Only when the low is greater than high. If that's the case, then we are returning -low -1. Otherwise, now we have a possibility of this. We have some elements left in the subarray to search. For that, we always compare with the middle element. How do we find the middle? Well, let's declare mid as an integer variable, which we can compute as low plus high divided by 2. That is going to be an integer value. And now we will look into 3 cases. Case 1, if the key is less than the middle element. If that's the case, then we need to do recursive binary search on the left subarray. Why left subarray? Well, because our low did not change, right? The low we are keeping as such, but the high that we had, right, has been changed to mid -1, right, which will ensure that we are searching for only left subarray. Okay, how about the second case? Now in the second case is the base case, where if key matches the mid element. If that's the case, we would return mid as the position. The third case corresponds to the key to the scenario where the key that we are searching for is greater than the middle element, right? For that, we'll do recursive search on the same list. It's the same key we are looking for, but we are searching in the right subarray. How did we enforce that? Well, the low that we had, right, has been updated to mid +1, right? So now it will take us to the right subarray, and our high did not change. All right, great. So now let's look at the final example of the recursive program, finding the greatest common divisor. So let's take some example. When you have to find out the GCD, or the greatest common divisor, of 2 and 3, then that is 1. Okay, in the case with 2 and 10, we know that 10, if you factorize 10, then 10 can be factorized as 5 multiplied by 2, and 2 is 2, right? So between 2 and 10, you will find 2 as the greatest common divisor. Let's take in more. Let's have a look at more examples. 25 and 35. So 25 and 35, right? So you can factorize 25 as 5 multiplied by 5. 35 is 5 multiplied by 7. So here the greatest common factor we have is 5, right? So GCD is 5 here. For 2 of 5 and 5, we have 5 over here. Now, how can we find the greatest common divisor? There are multiple ways in which we can do it. Our interest here is in recursive approach. All right, so we will define this recursive GCD method on two parameters m and n. Now, how do we do that, right? So let me tell you the concept behind that. So the procedure is like this. Let's take this example of 25 and 35. So what is done in this case, right? So here, okay, this is m. Okay, let's call this m and this n, right? So what we do in this case, we divide m by n, right? We do m n, right? So let's do this process and then we'll see the recursive procedure. So in order to find out the GCD, I will divide 35 by 25, right? It goes one time and you are left with the remainder, which is 10. Fine. So since the remainder was not 0, we need to continue this process, but now our divisor will change. Now the divisor will be the remainder, and I will divide the divisor that I had earlier, right? So now, since earlier my divisor was 25, now I'll use 25 as the number, and I'll divide that by the remainder that I have here, 10. Okay, so when you divide 25 by 10, it will go 2 times, right? You will be left with the remainder 5. Now what I'll do, I'll take this remainder 5 and will divide number 10, right? So why I continue to divide? Well, because the remainder was not 0. Remainder was non-zero here. So in this that was the first division, second division, and the third division. In the third step of division, when I divide 10 by 5, right, then it goes perfectly 2 times. I'm left with the remainder as 0. Now when you're left with the remainder 0, then that divisor that you had will become the GCD, right? So this is the approach which we use in the recursive formulation of GCD. All right, division. All right, so here we have that formulation for the recursive method of GCD. Now if we have two numbers m and n, and we want to find out the GCD of m and n, then the greatest common divisor of m and n will be n only if when you divide m by n, the remainder is 0. Example, well, if I want to find the GCD of 10 and 5, right, then this is 5 for the reason that, you know, 10 remainder 5 is equal to 0. Okay, so that's the first case, which is the base case here. Otherwise, what will happen in the other case, when you have to find out the GCD of m and n, then that will be the GCD of n and the remainder of mn, right? So this is what I was showing to you with the help of this division operation, right? So as an example, GCD, what did we do? 35 and 35 and 25. So when we had to compute GCD of 35 and 25, then how did we do that? Well, for that we would do GCD of mn is same as n, which is 25, and then 35 remainder 25, which was 10, right? And you'll go on and do it the same way. That's what I did in the previous slide. Okay, so when you know this recursive formulation, then writing the recursive GCD becomes a lot easier. And here is the code, right? So you have the public static int GCD defined on m and n as the two parameters. If m is perfectly divisible by n, that means if m remainder n is equal to 0, then you return n. Else, what you do, as you'll recursively call GCD on this n, right, the one that you are using as a divisor, and the remainder of the division operation, right? And this is the recursive call. All right, so I should stop right here. Thank you.